Welcome to Build with DynamoDB. My name is Eden Zulich. I'm a solutions architect focusing on NoSQL on DynamoDB specialist team. And with me today is...
Hi guys, my name is Sean Schreiber. I'm a DynamoDB Special Solutions Architect, same role as Eden. And today we're going to walk you through NoSQL Data Modeling Part 2. We've kind of settled on a format for today. We love to tell you some exciting new things that have come from DynamoDB in the recent past, including one of our most popular updates, one that has had the most retweets on Twitter. Customers are super excited about this very first new item released from Dynamo last week.
Yeah, so DynamoDB Adaptive Capacity might be something you already know about. We're super excited about the feature, but now even more so that it's in fact instant. So just as of this last week, I think, right, we announced that adaptive capacity is now instant, which means that the lead time that it needed to react when it first came out is not necessary anymore, and now it basically acts instantaneously on your tables. And as before, of course, it's there and it never goes away. So what that means is that as your application traffic workload changes, DynamoDB adjusts per partition provisioning dynamically to accommodate your traffic fluctuations. Now, one thing that I'd like to point out, I think we're super excited about the fact that it's now just working like that, so very seamlessly, basically, right?
Precisely, it's instantly. So Dynamo Adaptive Capacity is what basically allows you to use the amount of capacity that you paid for in the provision throughput model. So we used to have this slide that we would present, and it would show, okay, here's where throttling begins, here's where adaptive capacity kicks in. And that gap was anywhere from 5 to usually closer to 30 minutes. And now it happens in a split second. And so the truth is, with adaptive capacity, when we say it's instantly available, it means that it is always available, is always running.
It's always on.
With zero reaction time, yes.
Right.
And so that's a feature that was released without any impact to end users. There's no requirement that you upgrade your DynamoDB API version. It's available in all regions. And
on tables as well as GSIs.
On tables as well as global secondary indexes, exactly.
Yeah.
And one of the reasons why we were able to release this is that we had so much development work that went into on-demand capacity, which allows you to only pay for what you use. And so we took some of the technology and applied it to provision throughput
provision
tables.
mode. Yeah, exactly.
Precisely.
Yeah. And one thing that I'd like to point out about that is that, of course, there's still limits on what a single partition can do. So not to be confused.
Yeah, that's a very common question. So, Eden, adaptive capacity, now that's instantly available, sounds like it's it may even make partitions irrelevant. That's what I had a customer ask on Twitter late last week. So are partitions still important with adaptive capacity now that's instantly available? What are some of the things that we need to keep in mind?
Right, exactly. But you can see sort of if you step back and look at what has been done with the service over the past couple of years, you can see the trend basically that really goes towards completely making all this transparent and super easy to use, right, for different kinds of workloads. And that's really kind of what we're looking at here. This is one step on that path.
So, Eden, let's say I have a table and I've got 10,000 WCUs on it, which are write capacity units, which would let me write 10,000 1 kilobyte rows every single second. If I had a table that I had today and it had this adaptive capacity feature, of course, because that's built in, would I be able to say update a single row 10,000 times per second?
Right, that's a good question. No, you could not do that, right? Because a single row could still only receive up to 1,000 or consume up to 1,000 write capacity units. So if you're talking about updates that are consuming one write capacity unit, then you can only still drive up to 1,000 write requests to a single row.
But if I had a situation where I had 10 rows and I had to send 500 requests per second here, 500 requests per second per second over to this partition, but I only had half as much or even a quarter as much provision capacity, this is where adaptive capacity will come into play.
Exactly.
You no longer have to rebalance capacity on the back end on Dynamo.
Exactly.
It's available instantly.
And this is really great because it allows us not to have to worry about managing our partitions as much, right? We can scale out and increase the number of partitions, and DynamoDB will dynamically just manage the traffic workload as needed. So very cool. You also want to tell us about something else.
Oh yeah, so I'm really excited about this. I like the EMR DynamoDB connector. So I know it sounds like a whole bunch of letters put together, but it's called in GitHub. We'll throw a link up there. It's called the EMR DynamoDB Connector. It is a library that is open source, and it's what allows you to back up your DynamoDB data to S3. So if you are using something like data pipeline to export your table contents to S3, and this is very common for customers who have like analytics jobs that run in the background. For example, I have a customer, they store their review data for all of their properties, and so they have to track all these relationships, like who's the reviewer, who's the reviewee, which is the owner, and then what was the entity that was reviewed. They want to be able to establish links between all of that. In order to do that, we're talking about a lot of data processing. So they run these EMR jobs to back up data to S3. And a problem that customers had is that this connector didn't support on-demand capacity, because on-demand doesn't have a preset amount of units. Instead, it's based on your account limits in that region. And I believe, what's the limit in, the Northern Virginia region for DynamoDB write capacity? Is that 40,000?
I would say it's 40,000.
40,000, I think, is
Easy
the
to
default
check.
limit.
Yeah, but
So-
I think that is the default.
So then with this limit, what we do with the new connector is we let you apply a percentage, such as 25%, and we use that, we multiply it by the table limit of 40,000, and we use that to set the ingest speed or the export speed from your DynamoDB table. So this is enabling getting this data into S3 so you can query it via Athena. It's putting it to S3 so you can query it via Hive or HQL. Once it's in S3, you can also load it into Redshift or repartition it so that it can be queried easily with from Athena, say if it's in like Parquet format. So it opens up a whole wide swath of possibilities. And so the reason why this is our big announcement is it's not available yet in EMR, so you have to go grab this library off of the GitHub repo, clone it, compile that jar, place it in S3 bucket, and then either change the object ACL or go ahead and create a signed URL and use that in your EMR jobs and your steps whenever you're trying to create these exports
A few extra
on
steps,
on-demand tables.
but well worth the extra effort if you really need the feature.
Precisely. Unblocking those customers who
Right.
really want to use that on-demand capacity.
Right. Awesome. So before we jump into the new content for this session, I'd like us to do a quick review of what we went over last time. So we talked about denormalization and aggregates as some of the key concepts in NoSQL data modeling, right? Going from relational database where we have multiple tables to NoSQL where we have aggregates, right? And what are aggregates? Collections of related data that we read and write together. An example could be an order or a shopping cart, right? And we go from a normalized schema to denormalized aggregates so that we can take advantage of efficiencies that we get with NoSQL, where we have sharding and partitioning, right? So the idea here is that we reduce the number of requests that we need to make, whether we read or write data. So in this example, again from last time, we have our aggregates, orders in this case, that have a partition key, and the choice of partition key is here very important for evenly balanced distribution of not just data but also workload, right? And so each one of these is an aggregate, and so if we select this partition key such that we can horizontally scale, what we see is that as we add more orders and each order has a different partition key, we're able to scale this horizontally all day long.
I see. So we're getting more partitions by increasing our partition capacity, or we use on demand, and those partitions are fully managed for us.
Exactly.
So we can take this orders table from 100 customers that you might see in a month to 1 million customers 6 months down the line, which is definitely some of the growth plans that our customers have.
This to me is one of the greatest things about cloud native serverless database such as DynamoDB. It allows you to incrementally scale your workload, your database, right? So like you said, if I'm a startup with very little data at the beginning, as I grow, I should be able to just scale that seamlessly, and in fact, the whole point of this is how we do data modeling and design is to enable that scale and maintain that performance at scale. And DynamoDB is really good at it, but you do have to do a little bit of work in selecting that partition key.
Sacrificing a little bit of flexibility up front.
Right, exactly. And being aware of what your aggregates are. What are these data structures that we need to read and write together as a unit? And if we do that right, what we get is horizontal scale and performance at scale, because we always have a single round trip, whether we're reading or writing data, or very few round trips. Basically, that's the goal. And the other goal is cost. As we scale, and DynamoDB is able to scale, as we like to say, virtually infinitely. We'd like to manage that cost so that at any scale we have essentially reasonable cost. So partition key, to recap, good sharding partitioning scheme is what affords even distribution of data and workload as they grow. And again, back to the announcement of adaptive capacity, we still do need to worry about, or basically design our partition key so it can horizontally scale, because adaptive capacity can't help you magically shove all your partition keys in a single partition.
Yes, I had one customer place 40 gigs of data under the same partition key. Well, maybe at that point that's a little bit too much. I would say that Dynamo can always scale. If you want to put 40 gigs of data under the same partition key, you can definitely go ahead and try that. One of the concerns is if you need to access the data very fast, meaning read out megabytes at a time. And that can run into some bottlenecks because our fundamental unit is a partition. And what we found is in NoSQL workloads, you have hotkeys in any database. If it's whether it's Cassandra or Mongo, you're going to have hot shards. And in Dynamo, we surface those to you. But so you may think that you don't have that in your normal database. But if you go look, you see, oh wow, this one has a load of like 4, and it's like a quad core. It's got 4 threads,
right?
And so you're hitting the peak of what that server can do.
Absolutely, yeah. It's the same thing, right? Because they all work the same way. They partition data based on a partition key. So partition keys are the dimension of scalability. We talked about that, and about distributing aggregates across partitions. And so ideal scaling conditions, we covered all that. Another really important concept is how to accomplish data consistency with NoSQL databases, right? Common belief is that because NoSQL databases support mostly eventual consistency, that you have to compromise on your data consistency, and the fact is you don't. And
to your point, in terms of history, this I think idea that a non-relational database must be eventually consistent stems from that 2007 Dynamo white paper.
Right.
Yeah, which was written by Amazon engineers. Many of them actually still work at AWS. One, for example, is a general manager in AWS. And so that white paper explained it was an available and partition-tolerant NoSQL database. So we sacrificed the consistency in the CAP theorem.
Right.
And so that mindset, that legacy, because it was associated with the name DynamoDB, kind of a lot of customers project that onto Dynamo, and they think that it is not a strongly consistent service.
I usually joke and say that DynamoDB is a kind of a grandkid of Dynamo. I mean, there are basic concepts.
It's got better genes
there.
that have kind of come in over the generations.
I get, yeah, that's one way to, yeah, definitely interpret that. But the thing is, with DynamoDB, not only do you get strong consistency, right?
Yeah.
But you also have building blocks to make sure that you can implement transactional behavior, so that you don't have to worry about implementing services such as shopping cart, which are mission critical, right? You want to make sure that you have data consistency. So if you might be sharing that cart with a family member, you should still have expected outcome, whether you're both using it at the same time or not, right? And we do that using optimistic concurrency control, where and also using condition expression in DynamoDB to do check on the version. So we covered this last time, but I wanted to point this out because this is one of the key concepts in NoSQL, and this is how you do it in DynamoDB. And by the way, we also said, when you read a cart, you don't have to do strongly consistent reads, because the correctness of this approach does not depend on these reads being strongly consistent. Because what happens if that version check fails, right? You go back to you redo the basically step, right? You have to retry the.
And then there's one fundamental Dynamo that makes this possible, and then there's one common question I get, and I'll ask you that question here after covering the fundamental. The fundamental is that in Dynamo, data is always stored in 3 facilities or 3 availability zones. So when we accept a write, we coordinate that write, and we can do that consistently. We store that data in 3 places, but when we do a read, you can tell us to grab any one of those copies. And if you don't ask for a strongly consistent read, that's what's going to happen. A strongly consistent read is going to take you down to the coordinator, and we're going to be able to give you that exact row back. So a common question, Eden, that I'm asked, you tell me, do I consume any read capacity units whenever I use my condition expression?
Right. Well, the answer is it depends whether you're doing reads or writes. If what you're doing is reads, you only consume read capacity. And if you're doing writes, you only consume write capacity. So if I'm doing a condition...
Write capacity, reads capacity. So you won't use 2 types of units in the same request, because all Dynamo requests are either writes or reads or control plane.
That's exactly right.
Okay.
Yeah. So also we talked about relationships. So, NoSQL, right? And so, we have relationships. Yes, we do. And we implement those in DynamoDB using a key value access pattern on a table or GSI. One-to-many relationship, we use partition and sort key. We use that modeling basically either on a table or GSI, right? And then we use query API typically to read data. And then for many-to-many relationships, we model those using a table and then what we call inverted GSI, where we have a GSI that takes the sort key from the table and uses that as the partition key, basically. So even though we're talking about NoSQL, we can still implement and work with relationships. And one of the examples later on will actually show how to do that. So to recap, again, what are we trying to accomplish? Good performance and reasonable cost at any scale, right? That's the kind of goal of these design exercises, data modeling for any non-trivial use cases. And now we know that we can model relationships and we can maintain data consistency on updates as well. So for this to really be able to do this, you need to know access patterns for reads and writes. We need to know data size and shape in order to be able to figure out what our aggregates should be, right? And data velocity. What are request rates? How often do we do a particular request? What are peak rates for a given request? So if you remember last time, we went over this shopping cart service example, and we talked about modeling this as a key value access pattern.
And this is based on a real customer. Customers are our main focus here at AWS. Right. We based our roadmap on our customer feedback. So a lot of times we're not able to share who the customer is, and this happens to be one of those examples. But what we bring you here is ideas that are based on real world scenarios from the design reviews that we've done.
Yeah, absolutely. And in this particular case, we do of course, as always, need to know what kind of data are we dealing with, so we know, and we know how much data there is. We know data size, and we talked about it's under 1 kilobyte. We also know the total data volume in the worst case scenario and at scale. So in this particular case, this turned out to be up to 100 million cards in a table, and then peak.
You were saying there's peak throughput?
Yeah.
Yeah. And so what I'm hearing is 1K rows. Each row represents a shopping cart.
Right.
You can have 100 million shopping carts. And
at maximum,
yeah,
right?
maximum.
At
So
scale.
that's about 100 gigs.
Right.
So that table may have like a maximum size. Kind of sounds like there may be a situation where these shopping carts are expired over time or
exactly
or cleared out.
Right. So most of the time, what happens, and in fact, this is really something that always helps, is knowing sort of your application patterns, right? In this use case, the customer knew typical pattern is most people go on their e-commerce site. They put something in their cart and then they check out. However, there's a certain number of people who leave items in their carts, and that's fairly typical. I've done it as well. But
cart abandonment is a real thing. It's a statistic that you want to track in your analytics software.
Exactly. And in fact, in their case, what they wanted to do as a secondary use case, this is something we did not talk about last time, but in fact was part of the requirements that they had, was implement a price change notification. So for all the carts that are sitting out there, if items that are out there in carts get a lower price, let's say the price goes down or changes in any way, they wanted to be able to update those customers with a new price. And so what it meant, they had to read the carts and figure out which carts that are still out there have those items. And so we did rounds of iterating on that design.
You know what? I've heard something like this in social media. I've heard of this shopping tip where what you do is you go to a website where you want to buy something. Maybe you don't even log in. You just let the ad tracking take over. Then you go find that thing that you've wanted for a long time. You add it to your shopping cart, and then you don't check out. And then what can happen is they can link it back to an email address, and you may get an email notification with a coupon, so you can take it back and then finish that checkout and complete your purchase. And so if we're doing like these price change notifications, it sounds like a great way to even personalize the notifications that you're sending to a user, because if someone is anonymous and they log in, they add something to their shopping cart, and then you can find, the price went down, send a notification, say, hey, that thing that you wanted some Windex, a case of Windex for $11.99. Well, it's $9.99. Buy it now with 1-day shipping from Amazon.
Right.
Yeah.
And that's the basic idea, right? So then we said, wait a minute, but we have a data model for the basic scenario which works really well, scales well under pressure, right, for reads and writes. But now if we need to implement this price change notification, how do we find those items? They're now essentially buried in those carts. And do we change the data model or not?
How do we shrink our haystack to get down into just those carts that
basically
we need to know?
that was one question. But however, one of the interesting points to me was that velocity here. How often does this happen, right? Was one of the key questions, right? And this turned out to be a very infrequent occurrence, right? Maybe once every few days, once a week. And so when we talked about it, this is a fully internally driven, right, batch job, so to speak.
Like a regularly scheduled batch job.
Regularly scheduled batch job. And I thought, well, let's just do simple math. What if we just scan the whole table and see what happens?
I see. So you're going to, similar to the EMR DynamoDB Connector, which I mentioned earlier, and kind of tend to mumble that phrase even, but you're extracting the full contents of the data, running through your application, and then looking for particular things, right? Because
if you remember, if you watched the last episode, the data model was key value, and so our cart items are essentially in a map, in a JSON structure of each item. I can't have a GSI. And I probably don't want the GSI either, right?
So you can, if you don't know the exact partition key in Dynamo, you can't read the data out. You have to go with the scan, capital S, scan API to get the full contents if you don't know the key. That's part of Dynamo's, how Dynamo scales. We use that consistent hashing scheme. We take that key, run through a one-way hashing function, and then, as you saw in the slide earlier, we use that to determine, which partition it falls on. So
Right.
scan makes a whole lot of sense in this case.
Yeah, exactly. And so just as a simple, almost like a back on a napkin exercise, what would this price notification job cost in DynamoDB if I wanted to scan that table? So the worst case scenario, right, is 100 million items that I need to scan once a week, right? And I can take my time to do it. Turns out this was not time critical. We could take 24 hours, 12 hours, or however many hours. In fact, the nice thing about DynamoDB, I can change that provision capacity to the amount of capacity that I need for this batch job, and then do it, right?
And maybe and this makes a lot of sense because you want to spread it over time. You don't want to queue up 100 million emails to send through your MTAs,
That's the other thing.
in just 5 minutes.
Right.
Dynamo could do that. You could actually increase your provision capacity and scan the whole table as fast as you'd like.
Exactly.
Yeah.
So
And it's going to be the same cost, right?
yeah, exactly. Because the amount of reads and writes that we do in either case actually stays the same. The total amount of reads and writes is the same. They're just spread out over longer or shorter period of time. And so it turned out this cost $22 per batch job, right? So once a week you would have to incur an extra $22 in DynamoDB cost for this service in order to implement the price notification job by doing the table scan. Turned out this is very acceptable. We did not have to change the existing data model design. In fact, we did not have to compromise on the ability to scale on the shopping cart for the most important requirement of this use case.
So in this case, by using scan, you actually still have flexibility. So if you come up with a requirement later that you need to send these emails in batch, you can just do a scan after the
Exactly.
fact. Yeah,
Right.
So even months after you release a shopping cart.
Yeah, and so the point really of this story is really to show how that velocity plays into our design, and how cost plays into it as well, right? This design is influenced greatly by not just what we needed in terms of technical requirements, but also in terms of cost, right, to get it done.
Never had a customer said they want to spend more money on AWS.
Or on anything for that
That's
matter.
why we have our price releases, our price drops as frequently as we can, and we try to delight our customers in that way. Yeah.
Right. All right. So let's move on. Talk about item hierarchies real quick. This is something that is very important in data modeling in DynamoDB.
And so at this point, we're well into this is the new content for this year, or
Right,
sorry, for this
exactly.
episode.
For this episode, right? So item hierarchies are a way of organizing your data in DynamoDB so that effectively what is your logical view or record in DynamoDB becomes multiple items, and we have a way of organizing that in a hierarchy, right? And that's what we use composite sort key for. This is where sort key really comes into play, and depending on how we organize this sort key, we can be very selective in how we query and also on the one hand, but also how we write data on the other hand.
So we're sorting data based on the sort key on disk. So that's
Exactly.
like a lexicographical sort based on what looks like a string data type in this example.
Exactly.
Yeah.
And in this particular example, we're storing several types of products, right? Books, music albums, movies. And as you can see, we have a product ID, and then the type is basically the sort key in this case, and it could be a book, album. But then we also see hierarchy in case of albums here, where we have tracks. For movies, we have actors. And this allows us to update these individual tracks or actor records, right, without having to access all of the movie data or the entire album data, right? So this can save us on writes by allowing us to have this finer granularity, but we can still take advantage of the fact that we have this hierarchy if we need to access the entire record for the album. Let's see how that works. So query, product ID 2, and sort key is album ID. So exactly album ID, and I'm getting that basically main record for the album. I'm not getting tracks. I'm just getting the sort of the metadata for the album itself. On the other hand, if I change that sort key to use the begins with function on the sort key, and I basically say sort key begins with give me all the items that begin with album column track, then I'm going to get only my tracks. And I can also go all the way and just get query on the particular track. And another example is if I want the entire album with tracks, I can simply say give me all the rows, all the items for the product ID that I want.
Yeah. And in each of these examples, we're using the query API in Dynamo, capital Q query. So that word actually means something very specific in Dynamo parlance. And the only requirement there is that you know the partition key. So you don't,
Right.
and so we're just using that sorted nature of the data on disk using the sort key. You know, a question that has been asked in this case on the chat by Destroyer. I want to call you Destroyer September 10th, 2019. You know who you are. The question was about how can we get data back in a different sorted form. And if you want data that's sorted differently on disk with the same partition key, what we would recommend is a global secondary index. You can create an alternate global secondary index.
Right.
And so those are like DynamoDB tables, but they're shown under the index tab in the AWS Management Console. They have provision capacity, read and write units, or you can enable on-demand mode.
And we just call them GSIs, by the way, for those of you who are new to DynamoDB.
Good old GSIs.
Yeah, and they really are a different view into your data. So we call them materialized views, right? Every GSI is a different materialized view. And why is that? It's because you can change what you partition on. And so when you decide to partition on a different attribute, your data for that GSI is stored based on that new partition and optionally the new sort key. And so if you do want a different sort order, that's what you would do.
And another question is, if I only want back the, say the album length, how would I do that on the APIs? So that would be, how do I query out the data but only get a single attribute? Well, one thing I'll add, and I'll let you complete the answer, is that even though you're retrieving a section of the row, you're still paying for the whole row to be read from disk. Yeah.
Yeah, so for that, you would use the first query, the green one, where you would do the product ID, basically, and then the sort key would be album ID in this, or album. In fact, the word album. And that does get you the entire row. You could have a projection, though, to filter out the attributes.
Projection expression.
Right.
Yeah. So
However, as Sean, as you just said, you would still pay the RCU amount that's equivalent to the entire entire item. So alternatively, you could create data hierarchies that also use JSON documents. And what that would look like in this case is majority of the data would be simply JSON document, and then we would maybe have some attributes, maybe those attributes that we need to have another global secondary index on. Those would be top level attributes, because you can't have you can't have GSIs on nested attributes in JSON in DynamoDB.
So Dynamo is technically a multi-doc or multi-data, whatever you want to call it. It's a key value and a document database.
It does have document API.
Yeah,
yes.
it does have some of those APIs. But then when it comes down to indexing documents, the keys have to be extracted or copied to the top level. So you have to have a top level attribute.
Right, exactly.
All
Next, GSI overloading.
Yeah, so now we're going to talk about GSI overloading. So GSI overloading, the concept is you create a single GSI and you call it something like, GSI PK or GSI PK1, and then you have all different types of documents sitting in that GSI. So what we have here is like an HR record. So we've got the employee name, the year. We might have some information about quotas. We might have some job titles and other information like that. So we have a sort key that's in here that's native to the data, and what we're going to do is pull that out and call that the GSI primary key. And so what we're doing here is instead of saying employee name is the attribute name, we're just saying everything is going to have GSI PK1. Every single row is going to have a GSI PK1. And then you're going to read out that value. And then from the value, you're going to infer what type of record it is. So you might have the ability to, on a GSI, each of these is going to represent a different row. So you have one row for the employee name. You're going to read that out and get back the employee name and some other information about them.
Right.
Yeah.
In
Employee
fact,
by name. Exactly. Yeah, that's it. You can find the top performers by quarter. And so when we say we got that year and that quarter, that's like a quota amount. So you're going to be able to see for that key, do a query and get back the value. And the reason why this design is so important is instead of having 10 GSIs or 20 GSIs, you can just have a couple of GSIs and overlap the attributes. One thing that I've seen that's very common in our design reviews now is, and I'm sure you've seen this, we don't even call the primary key what it actually is. We just call the primary key or the partition key the PK.
Right.
The sort key is just the SK. So when we go to Excel and we start our designs, it's always a generic name.
Right, and it can mean different things in different sort of contexts, in different types of data, because we might be sharing that basically attribute between different types. And so in this case, we have this attribute called data. So the other thing about GSI overloading, now that you can have up to 20 GSIs per table, not that much of an issue. But you know what? GSI overloading kind of helps keep the cost down too, right? By overloading that GSI, I don't have to make another GSI. I can reuse that same one for different types of queries, and that's pretty cool too.
And so a lot of times I would say GSI overloading, that concept is kind of related to an item hierarchy, because I see some customers, they'll either go with the GSI design that has a GSI, or instead what they'll do is they'll just use a regular DynamoDB table and write like multiple rows, different entities under the same table. And I think we've got some examples that get into that as well. So it's not just item hierarchies, but there's a lot of these concepts that kind of overlap. But you don't even need to go with a global secondary index. It's not like we start by default that you're going to have a GSI. If you have like a many to many relationship, there's plenty of ways to do it.
Right.
Yeah.
All right.
Right sharding is another interesting concept. Yeah. So the theme of this of the show today has been performance, and at the lowest cost, let's optimize on the cost. Right.
Designing for performance and cost, right?
Yes, performance and cost. And so how do we get the full performance out of DynamoDB? Well, what we've seen in our custom workloads is that oftentimes there's always a slight imbalance. I mean, it's just the nature of the world. I had one customer, their version of a hotkey would be a tractor getting stuck in a field and left in that position overnight. And then the partition key was a geohash of the quadrant of the field. And so it's reporting at 5 hertz, 5 times per second. All of the data, it's all going to the same DynamoDB partition. So tractor gets stuck in ditch, and now we've got a hotkey, right? Right. So how do we handle that? And so what we look for is, as a basic design tenet, is keys with high cardinality. And sometimes that's not always the case. Tractor stuck in a ditch, for example. Right. We also want these to be spread, or in that case, it's really, the second part of that is really, if you have 1,000 tractors, that's great, because you have some high value of keys. That's a high key cardinality. But if you only have one make of tractors, let's say you are a company who makes tractors, and so the make is that. If you want to create a table where that is a partition key, the make, I'll call it Acme, that's an issue because low key cardinality, and also you're going to have a lot of rows going to the same partition in Dynamo.
You can't really horizontally scale that.
Yeah. And so the point is we realize that it may not be possible. So how do you take something that's kind of imbalanced and put it into DynamoDB? Well, we have this method called scatter gather. Right. And the idea behind scatter gather is we take something we know, which is a partition key that is known to us, and then we go and right. And then we use that to figure out where the data is going to go.
First, what happens when writes are not well distributed, to drive the point home?
Very important. Yeah.
You end up with just more data per single partition than you can have.
This is this example of a customer I mentioned earlier where they put 40 gigs of data under the same partition key, and this creates this heavy pressure on Dynamo. Dynamo will always split out and add more partitions to give you that scale, but there's definitely limits, you know, in terms of throughput. Can you actually read it back fast enough?
And it really goes back to all NoSQL, sharded databases, right? There's only so much you can do with a single server, with a single node. That's kind of really one thing to keep in mind. Anyway, so
when we have this value that we know, in this example, we're just going back to that x value. What we know is there's going to be many values under this. Let's say this, X could be the name, the manufacturer of the tractor. So that'd be Acme. So how do we spread that across all of our Dynamo partitions? So right sharding, enter right sharding. Right sharding has in this strategy, a set number of shards or possible key values where the data can be placed in. So when we write data, we're always going to pick a random number between 0 and n. N could be 8, it could be 10, it could be 100, depending on how much data you're putting into Dynamo. So you have to randomly pick that. And then on read, you have to do that many queries to get all your results back. So after we run into that hashing, we're going to place them on the partitions. We're going to have to read and get all those values out using the known values. And so what we can call this is a simple right sharding, based purely on a preset number of buckets that you might put in your code or you might store in a configuration file. Yeah.
Right.
And the other design, this is one that's not well understood by our customers, I think, without having a design like this in this format, which is great. So we can show you an illustration of where the data goes. Without that, it may be a little confusing. So we have this idea of creating a calculated partition key. And so the calculated partition key relies on a couple basic primitives. First, we have a hashing algorithm which is going to take a string value or a number value and convert it into a set of bits or to a number, depending on whether it's the former or the latter. So we're taking something that could be in any format, and then we're converting it to a number. We're doing that because we want to do some very basic math. We want to take, say, a string representation of Acme, convert it into UTF-8, get the integer or the long that represents that, and then divide it by 200 and get the remainder. And so we've got 200 buckets where that data can fly or can fall into. And so the great thing about this is if, I have a brand of like Acme or whatever it may be, I can drop this in and I can see exactly which partition the data would fall under. Or maybe, serial number would be a good one. So if it's under Acme and then, we have got the serial number, we can calculate that serial number and say, that's going to be on this shard.
Right, and so in one hand we completely randomize that. So and now you might be wondering, well, if it's random, how do I access those individual records? And that really works in cases where you don't need to access a specific record, but you really need to query the whole essentially collection of those items, right? And in this case, where you have a concrete, essentially, basically salt that's calculated, it allows you to access those records individually.
Precisely. And so we have the same end result where that data is distributed. And in some cases, you can figure out which bucket a given key is going to be in. And in others, you just need to query all 20 to get the data out.
Exactly.
Yeah. So,
I mean, some cases where that really makes sense might be if you're a multi-tenant, if you have a multi-tenant use case, and let's say your tenants have all these events, and for the primary use case, you might be sharding your table on event ID, and it's all really well distributed, well balanced. But on the other hand, you need to be able to access all events that belong to the single tenant account. And so you might have a GSI on, let's say, account ID. But the question now becomes, can that GSI sustain the right throughput of those events? So if the rate at which these events are coming in is greater than 1,000 write capacity units per account, your GSI will start basically sending back pressure to the table, right? Because it can't handle more than 1,000 write capacity units. And in this case, the randomized sharding makes sense because what we really need, the access pattern for the GSIs, give me all the events that are basically that belong to this particular count. And that's one use case. In fact, one scenario where this comes into play more and more is GDPR, where you simply need to be able to access data based on a count, for example. And so selecting the number of shards, right, is another thing that you do have to figure out in this case. That number of shards really should allow you to accomplish the scale that you need.
Right, and we would generally recommend that you put that data in a configuration file, that it be able to be increased, that you have a single place where you can increase it. And then for the advanced users, you may want to identify which of those collections, which of those keys are sufficiently large enough to need that right sharding. So you may only shard the large tenants or the large teams, depending on the use case. And in that case, you probably create like another Dynamo table, and in there you would store the metadata. Like this partition key has 5 shards, this has 10 shards. And if you need to increase it, you just increment that by 1 using the write conditions to increment it, and then now you've got 11 shards instead of 10. So you always want to be able to change the number of shards. You can kind of pick a value, and then you can always use a Dynamo table on the side to store the metadata about the shards, kind of purely on the application side. It's not a feature that's supported directly by Dynamo write sharding. Yeah.
Right.
So that's that. You mentioned, Eden, earlier the concept of what do you do when you have a lot of values going to the same GSI partition. And now we have the concept of GSI write sharding. So in this example, we've got a GSI primary key that's set, and we have all these rows that are flowing in, and we want to sort our statuses. So we've got info, critical, and warning, and so we want to be able to say scan everything and get like just the statuses back. That's the start of creating a GSI. It's one of the things you can get out of a GSI. But perhaps we want to just find all of the items that are in critical state. And so what we'll do in this example is we'll create, say, 5 shards. Our partition key is going to be 0 through 5 or some value like that. And then we do 5 queries at one time, and we say begins with critical. And we can get back only the rows on the partition that are in the critical state.
What this also does for us is it actually allows us to have the data that we need to access sorted, and then we can access all those rows that have state critical easily.
Yeah, right? And in this example, as you're saying, it was sorted, so we could get everything that's in critical that was created in the last hour. We can do a betweens with our query operation to get everything's critical between this date and that date.
Right.
And so that's just the beauty of GSIs with the sort keys, the data sorted on disk, ready to go.
Right. All right, that's cool. And next, we have an example modeling a movie database. This is just an example. I thought about this. One of the tutorials, if you remember, those of you who watched the first episode, we have a tutorial that takes a movie database, and it's partitioned on year and title. And I thought, okay, what if we iterate on it and do it a little bit differently, maybe a little more realistic. We're not gonna do the entire data model with all the entities that might be there, but let's start with movie actor and director, and see what that would look like in DynamoDB. And we might run out of time with this example, but if we do, I think we can just continue next time.
Yeah, let's see what we can do.
Yeah.
So we like the idea of the movie actor director because there's people who can be actors and directors. It's never that simple that they're just an actor, right?
When I started, I didn't even think about that, right? So I just modeled those as different sort of independent entities, right?
Mm.
And speaking of which, what's an independent entity, right? It's an entity that can exist in its own right. So an actor exists whether there are movies or directors, right? As opposed to maybe your
How about a headshot of an
headshot,
actor?
exactly,
Yeah, that
or a
you go on
thumbnail.
IMDb, a lot of times those actors' pages are maintained by their agent or their publicist. So
Right.
that picture is usually only of them, so only be associated to their actor profile, not to
So
like the movie they were in.
that would be a dependent or a child entity, because when I remove that actor, I also want that headshot to go away as well. By contrast, if you have, let's say, screenshots from movies with multiple actors, those might be independent entities, top level entities that basically should still be there even if one of those actors is removed from the database, or maybe even if a movie is removed from a database. So there's a way to model both, basically.
And so it seems like for this design, what we've had to do is have a movie, and a movie is a movie. There's that's a pretty tight relationship, but the same person can be both an actor and a director. So in NoSQL terms, what we've had to do is create one representation for the director and one for the actor, which does duplicate some data. For example, the actor's name.
That's right. That's one approach. And one other thing actually that we did with this is, let's say you're a movie buff and you're interested in what directors an actor has worked with. And by the other way of that relationship, the other side of that relationship would be if you're a director, what actors have you directed, right? And so here entities are identified by the partition key.
Here's our initial design for how we would do this.
Right. Basically, we have a movie partition, and then actors and directors. And so if you look at the top row for the movie partition, you'll notice that the sort key, in fact, is identical to the partition key. That's just by that's a conscious choice in this case. It could be something else, but what it cannot be is any other entity, right? Because that particular record is the entity metadata. That's the record of details that are specific to movies only, right? And that's what essentially distinguishes this as a top level entity, because
the entity record of the entity item.
record, right?
Yeah.
Exactly. And we have the same for actors and directors.
And to be clear, each of these rows with different sort keys, those are different Dynamo items. So that's one put item, another put item, or a batch rate item to put up to 25 of those at a time.
So the yellow items that are basically colored in this diagram, right, are relationships which in fact take both the movie, so as one entity, and then the other side of that relationship is the ID of either actor or director. And that's how we establish and maintain those relationships. So relationships always have two basically entities represented, right? One by the partition key and one by the sort key. And so now the question is, well, what data should we have for each one? And what do we get by having this relationship, right? And so this is where we essentially think about the materialized view, the result set. So if we're thinking about
NoSQL 101, start with your queries.
Start with your queries, right? And start with the most important access patterns, right? So if I'm thinking about the movie detail, I should have all the details about the movie, which are represented by, and in fact, before I get to the movie detail, how do I get to it, right? I have a partition key, and that's an ID. That's a unique ID, basically. And why is that? Why is that the choice of partition key? And that simply kind of goes back to the notion that we should have unique IDs and be able to avoid duplicates and in our data, right? But in order to find the movie, we need to have a GSI then. And we have a record, we have an attribute S name, and if we have a GSI on that,
And see, it says GSI PK on top. Yeah.
Exactly.
See on top
right?
of that table.
And once we have basically the name of the movie, then we actually have the movie ID.
Mm-hmm.
Now I can retrieve the record, all the details for the movie. And in fact, I can query that table on the movie ID and retrieve all these associated records. So actors that are in the movie. And then if I look at what I have as part of those records, I have actor name. And now you might be wondering, why do I have title of that movie again in that record? And I have it there for a different view, basically, for a different query.
Mm-hmm.
But I also have the name of the character in the movie. CO is the order, right? In the
That's the credit order.
credit order.
Yeah,
that's right.
I hear the actors always argue about that, and they try to get it, in their contract. I'm going to be credit order number 2, or some actors want to be the very last in the cards.
Exactly.
In the pre-roll, like at the beginning of the movie, they want to be
Right.
and featuring Steve Zahn.
That's
Actor I haven't
right.
seen in a while.
So, by the way, we're running out of time, and so
Indeed, we are.
we do have to stop here, but stay with us next time as well.
We filled up the maximum size of our NoSQL modeling row.
That's right.
We capped out. So we're gonna have to shard this.
Fresh out of capacity for today.
Fresh out of capacity. We forgot to switch to on demand before we began.
So next time we will actually continue and finish this exercise before we move on to the next topic in the series.
Absolutely. I think the great thing about this format is we get to experiment. We get to come up with designs that maybe you haven't thought of before and make sure that we're action packed. We give you as much information as we can in our time. So if we happen to have more information to share than there is time, I think it shows that there's a lot of interest in this topic, and that there's so much more that we can say.
Don't be shy. Be active in the channel. Let us know what you'd like to see, what you'd like us to talk about on the show, and bring your questions. Thank you so much, and we'll see you next time.
Bye.